Alright. So, all right. Good afternoon to all of you. So we are waiting for. We shall be waiting for 2 more minutes for more students to join, and then we shall start. Please confirm if the audio quality is fine. Yeah, if you have sent me an email this morning, I haven't checked it yet. I shall soon check it. So in any case, we shall start in few minutes. So if you have sent me your assignments, if you have mailed me your assignments, I shall check it today. So don't worry. So today we are going to look into different properties of Fourier transform, and I think this is going to be at least 2 parts. Okay, right? I have divided this into at least this is going to be divided into at least 2 parts, in my opinion. This might turn into 3-part a 3-part lecture. Okay, yes, I have got the for example, I have got the assignment from one of you quite a few days before. Yeah, 2 days back. Yes, I did get it. Yeah, but somehow I couldn't reply. Anyway, I will get to those, so don't worry. Right. So about this class, okay, we shall need at least 2 classes for discussing properties of Fourier transform. Right. Now we actually need to discuss properties of Fourier transform for different reasons. Okay, and you shall it will be soon clear what those reasons are. So that's one of the things. And again, I don't want to complete this topic in a hurry, so I shall take as much time as you people need and as I need to complete this. Okay, so this could be 2 parts. This topic could have 2 parts, 2 classes, or this could have 3 classes, right? Just because I want to complete these things, not in a hurry. Okay, because in any signals and systems courses, you need to study all the different properties of Fourier transform. Okay, because those are going to be of utmost importance later on. So with that understanding, I should tell you that there are quite a few properties, but once you are familiar with those properties, you shall understand that in many cases, under many situations, if you are calculating the Fourier transform of something, and if you are aware of all the properties of Fourier transform, then often what happens is the amount of calculation that you have to put into in order to calculate the Fourier transform of a certain signal is greatly reduced. For example, if you know certain properties, then a problem can be brought down from a 3-page long problem, okay, into a half-page long problem, for example. Okay, if you understand all the properties and if you have learned how to use those properties. And more importantly, often you shall see, as electrical engineers, we shall deal with more inverse Fourier transforms than Fourier transforms. Okay, we shall see more use of inverse Fourier transforms. And while studying inverse Fourier transforms, you will see these properties will come very handy, because doing some calculations directly on inverse Fourier transforms, I mean doing an inverse Fourier transform by means of doing that integral, often results into very cumbersome calculations and rather infeasible calculations often, right? So yes, I mean often we see that proceeding in the standard way, like doing everything from scratch, is not an option for anybody, right? So that is why we have plenty of properties of Fourier transform. Okay, so we do use those properties in order to better analyze and rather easily analyze properties of systems and signals. So that is going to be our agenda today, right? So with that said, let's start our discussion today. So as the name says, so we are going to dive into properties of Fourier transform. By this point, I am assuming that you already have understood where Fourier transform comes from, what it actually is. Okay, but before I proceed, let's recap in like 2 minutes. Fourier transform is nothing but the extension of Fourier series for aperiodic signal. While discussing Fourier series, we found a way through which we can figure out the constituent sinusoidal components present in a signal. So if a signal can be expressed as a sum of different sinusoids, then the constituent sinusoids, namely their amplitudes, can be determined based on using Fourier series, and that was applicable if the signal was periodic in nature. Then through exponential Fourier series, we did an extension of that, we did a generalization of that, and that generalization gave us something called Fourier transform, which does not assume the periodicity property of Fourier series, right? So if the signal, even if the signal is not periodic, Fourier transform is still applicable, and with that we can still figure out the constituent sinusoidal components. Except there is one major difference right now. The major difference is that when the signal is periodic in nature, the fundamental sinusoid has a frequency equal to the frequency of the original signal, right? So if your signal has a frequency of, say for example, 2 radian per second, then the fundamental sinusoid is going to have a 2 radian per second frequency, and all the next sinusoids would have frequencies that are multiples of those, right? All the harmonics, we call them harmonics. But in case of a aperiodic signal, frequency is no longer discrete. We don't have discrete groups of frequencies like 2 radian per second, 4 radian per second, 6 radian per second, and so on. We don't have frequencies like those. Instead, we have frequencies which are continuous in nature, right? So the minimum frequency we could have would be minimum absolute frequency we could have would be somewhat like something like zero, and the next frequencies are going to be infinitesimally distant from those, right? So we basically have a continuous spectrum of frequencies. But again, since Fourier transform is a generalization of Fourier series, any signal that is periodic also has a Fourier transform, and we eventually actually saw those examples in the last class, and we shall see plenty of other examples like those later on, right? So in any case, we use Fourier transform as a generalization of Fourier series. That's one of the important things to know. And since most of the signals that we encounter in real life, like most of the common signals, like even the unit impulse, those who study signal processing and those who do electrical engineering, for example, okay, for us most of the signals are non-periodic in nature, and so Fourier series is not that an useful tool for us. But Fourier transform, on the other hand, is quite an useful tool for us, right? So with that said, so let's start our discussion today. So this is the definition we have used. So this is the Fourier transform pair. We call it a pair. Okay, one pair of Fourier transform and inverse Fourier transform. This was the definition of Fourier transform for a signal xt. So this is what we derived. And I told you there are 3 other popular definitions of Fourier transform and inverse Fourier transform. But nonetheless, they are quite similar to this. So this was the definition of Fourier transform that we used. Okay, this is the continuous time Fourier transform, and this is then continuous time inverse Fourier transform. And again, anytime you have any difficulty understanding me, feel free to post a question here in the live chat. I shall be answering your question. Okay, and don't think your question is stupid. Okay, even if it is, apparently I shall still answer your question, because no question is actually a bad question, right? So this is the Fourier transform, this is the inverse Fourier transform, right? This is the Fourier transform and this is the inverse Fourier transform, right? So this is the definition we are going to use, right? So with that said, as I told you, this is the definition that is used by control system engineers and signal processing experts, right? And this is the definition you will see for the most part in your electrical engineering classes. But there are other definitions, namely definitions used in modern physics, like quantum mechanics. That definition slightly differs from this. Then other definitions which are used in communication engineering. So those who study communication engineering, for example, those who are in Department of Electronics, they probably, while studying communication engineering, do study Fourier transform in a slightly different fashion. Okay, because for us, the frequency is in radian per second, but for them, the major difference is that the frequency should be in hertz, not in radian per second. And then there is classical physics. In classical physics also, Fourier transform is quite useful, quite used rather, I would say. And there the definition is slightly different again. But this is the definition we use for our Fourier transform pair. And this I should tell you at the beginning, I have told you at the beginning, simply because just to have a reference point on which we're actually trying to calculate everything. Because all of our properties that we're going to derive today and for the next 1 or 2 classes, okay, all of the properties that we're going to derive will be based on this. So if you are using any other definition of Fourier transform, the properties that you derive would be applicable, okay, but with slight modifications, right? For example, there would be many 2 pi's, for example, in our example, okay, and in some definition that 2 pi might be omitted, something like that. Anyway, with slight modification, but in spirit, all the definitions, all the properties will remain the same. And again, this is the standard notation that is used by electrical engineers throughout the world. So don't worry about that. Okay. In any case, with that aside, so again, for example, those who are appearing for competitive examinations like GATE or anything, okay, so if a problem on Fourier transform appears, this is the definition that the examiners will be assuming, right? So paper setters will be assuming, so don't worry about that, right? So with that said, so let's talk about the first property that we are going to encounter. Okay, that's the linearity property, and we actually did prove the linearity property in our last discussion, right? Linearity. So I'm not going to prove this because we did prove it in the last class. Okay, so linearity essentially means 2 properties, right? One scaling property, right, and one superposition property, right? Additivity property. So scaling, so homogeneity plus additivity plus additivity, or rather superposition. Right? So again, the definition here of the notation here is that we often use a symbol like this. We often use a symbol like this. We write xt with a double-sided arrow. Okay, with a double-sided arrow, and we write x omega to denote that the Fourier transform of xt is x omega and the inverse Fourier transform of x omega is xt, right? So we use this notation, okay, right? So I think, this is understandable, right? So this is the notation we people use. In any case, the homogeneity definition tells me that if this is true, then the homogeneity property tells me that if I multiply xt with any number, for example, namely, say for example, a, okay, so if the Fourier transform of xt is x omega, then the Fourier transform of axt is a x omega. We actually established this in the last class simply because that integration was a linear operation, right? Again, linearity satisfies these, and this is homogeneity. We're not going to prove this because proved in the last class, right? Okay, right. So this is the homogeneity property, and the superposition property. So superposition property says if the Fourier transform of a certain signal x1t is x1 omega, and the Fourier transform of a certain signal x2t is x2 omega, then the Fourier transform of their sum x1 plus x2 will be x1 plus x2. Yeah, okay, right. So that is what the superposition properties tells me, and therefore linearity simply tells me that if the Fourier transform of x1t is x1 omega, if the Fourier transform of x2t is x2 omega, then the Fourier transform of any scalar multiple of x1 plus any scalar multiple of x2 and their sum, and you could have as many terms here like a1 x1 plus a2 x2 plus a3 x3 and so on x3. So sum them up. The Fourier transform for the sum would be a1 x1 omega plus a2 x2 omega. That's the linearity property. We actually did prove this in the last class, so I'm not going to go into the proof of this. All right, because this is again a very important property. For example, so if I have two functions or two signals added, I can split them if possible, okay, and separately calculate the Fourier transform and then add them back. So those kind of things are easily applicable here. So I don't think there is any issue understanding this. But then again, if you have any problem understanding something, feel free to ask. Now we are actually going into the more important properties rather. So again, more important. This is the most important property, linearity. Okay, if this wasn't linear, then we would have a lot of trouble understanding anything. Right. Right. So property number 2 is time shift. Time shifting. So time shifting property. So what is the time shifting property? So in the time shifting property, so before I prove it, let's write down the time shifting property. So if I know that the Fourier transform of xt is x omega, then the time shifting property tells me that the Fourier transform of x t minus a would be something. But my problem with me is that I cannot really recall any formula per se, but I can derive everything somehow. Okay, so let's try figure out, if I know that the Fourier transform of xt is x omega, then what is the Fourier transform of a delayed or an advanced version of t, advanced version of x, right? So if I have right shifted or left shifted the signal, then what is the Fourier transform? So let's have a general expression for that. So instead of calculating everything from scratch, we can in reality use a certain property of Fourier transform, which is a time shifting property we are going to learn shortly. In order to we can use that to calculate the appropriate Fourier transform for the shifted signal, okay, delayed or advanced signal. Notice that here a can be positive or negative. For this particular scenario, if a is positive, it's a right shift or a delay. If a is negative, then it's a left shift or an advance. Okay, so let's try calculating that. And oh no, okay, people had to start up right now. Right, so let's calculate that. So we are calculating the Fourier transform of this, right? So let's prove something. Okay, let's prove something. We are calculating the Fourier transform of this, and I'm just I'm writing a proof here, but I'm actually deriving it right now with you people, right? We are trying to calculate the Fourier transform of xt minus a, assuming that I know that the Fourier transform of xt is x omega, right? So with that said, this is what we are calculating. So by definition, yeah, again for attendance, just write down something on the live chat. Okay, good morning would suffice, or good evening, good afternoon would suffice, or good evening if you're joining late. But the thing is, write something, or maybe post a question if you have one. Okay. Okay, that's the definition of Fourier transform here, right? So we are calculating the Fourier transform of xt minus a, right? So with that said, if I do that calculation, I would need some substitution operation, right? I would have to do some substitution. So while doing integrations, you have studied substitution. So let's substitute something. Okay, so here I am substituting something, and this is going to be the substitute. So what is going to be the substitute? Okay. The substitute is going to be t minus a. So instead of writing t minus a, let's write something. Say, what should I write? Let's write p, maybe, I don't know. Okay, then dt of course becomes dp. Okay, and what about the limits? We have to think about the limits, right? Whenever we do a substitution, we have to think about the limits. So here I have t, here I have p. T varies from minus infinity to plus infinity, and when t goes to minus infinity, p also goes to minus infinity, because a is a finite quantity, right? So this is minus infinity, and when t goes to plus infinity, p also goes to plus infinity. So that is it, right? So with that said, let's substitute everything here. So this integration, again, the limit does not change. The limit remains from minus infinity to minus infinity, even though we have shifted everything to p. And x, instead of writing t minus a, of course I write xp. Okay, and e to the power minus j omega, and instead of t, I now would have to write p plus a, because t minus a is equal to p. So I write p plus a dt. Okay, right? So there is no issue with that. Also not dt, huh? dp. Right. So we have that. So we have this integration, minus infinity to infinity xp e to the power minus j omega p into e to the power minus j omega a dp. Now look at this integration properly. Okay, look at this integration closely. What is the variable in this integration? The variable in this integration is p, because that is what with respect to which we are actually calculating the integrals, right? So if the variable of this integration is p, then this quantity e to the power minus j omega a does not have a variable involved in it, right? So it is actually a constant term from the perspective of this integration, right? So I can take this term, take this particular term and bring it outside, simply because that this term does not have any variable term with respect to the integration here. So that can go outside. I have e to the power minus j omega a, an integration from minus infinity to infinity on xp e to the power minus j omega p dp, right? Right. So this is e to the power minus j so this is e to the power minus j omega a integration minus infinity to infinity. But again, try to understand what is p. P is nothing but a name here, right? Right, yes. P is nothing but a name here, right? Right? P is nothing but a name, and which is inside a definite integral. So improper definite integral, okay? So in this definite integral, improper definite integral, we have p as a name, right? So this p can be anything, right? This p can be whatever I want, right? This p can be any other name. It does not matter, right? Because this is just a name for the placeholder of the definite integral variable, right? I can write x, I can write y, I can write z, I can write t, I can write anything I want, right? A, b, c, d, whatever, right? So I can write t, of course, because that's a name we have, right? Right? I think that's understandable, right? So technically, let's go back, right? So I can write anything I want here, right? So I believe without writing anything here, you can say that this is just x omega. Simply because try to understand what is the definition of the Fourier transform. The definition of Fourier transform is this: minus infinity to infinity xt e to the power minus j omega t dt, right? But instead of writing t, I could as well write p. I can write anything, right? Because that's a placeholder name, because after the integration t will not be there, right? That those will be replaced by any expression involving p will be replaced by the upper limit and lower limit, right? So p will not remain. Just like if we had t will not remain, right? That is how the definition here works, right? Since this is the definition, for example. So with that said, I believe you understand that we have this, right? So please feel free to ask if you have any query. So what we have just discovered is that the Fourier transform of a delayed or advanced version of xt, so xt minus a, would be e to the power minus j omega a x omega. We are going to shortly do a problem on this, so actually you have a better understanding. But the problem with me is that I cannot recall any of these properties, right? Unfortunately, when I was a student, I couldn't recall. Now as a teacher, I still cannot recall. But I always made a point of understanding the procedure behind every problem here, right? So with that said, this is the property we are going to use. So quickly, so if you have any query, please feel free to ask. So again, try to understand that x omega is the Fourier transform for the original signal. Right. All right. If you have any query, feel free to ask. All right. So if you don't have any query, so let's do an example, right? Example. So question is, you already know that the Fourier, so I'm asking you to calculate the Fourier transform of a delayed version of unit step, this. So calculate the Fourier transform of a delayed version of unit step. So can anybody attempt that problem? So now again, you might have already understood that, handling this problem directly is an issue, right? Because while calculating the Fourier transform for ut, we could not directly attempt that problem. We had to go back to signum function, and here if I want to do something like that, I have to find out the Fourier transform for a delayed version of signum function. So we have to go through a lot of trouble, right? And those lot of trouble can be saved, okay, if I just apply a small property, namely the time shift property. So the solution would be somewhat like this. So we know the Fourier transform of ut. What is the Fourier transform of ut? We already calculated in the last class. It turned out to be 1 by j omega plus pi delta omega, right? That was the Fourier transform of ut. And this is one of the things I can remember because I have used this so many times. Okay, so Fourier transform of ut is 1 by j omega plus pi delta omega, right? That's understandable. So therefore, with just a single line without calculating anything, I can say the Fourier transform of ut minus a. So this is just a delayed version, right? So the Fourier transform of ut is this. Then what is the Fourier transform of ut minus a? So we have to apply the property, right? So this is the original Fourier transform, right? Now look at the property here. So if I have the original Fourier transform, then for the delayed version of the signal, the Fourier transform can be calculated as the original Fourier transform multiplied by e to the power minus j omega a. So what is a here? This 2 is the a here, right? So the answer would be e to the power minus j omega 2, right, into 1 by j omega plus pi delta omega, right? So simply this is e to the power minus j 2 omega 1 by j omega plus pi delta omega, right? So that's understood, right? I think that's understood, right? So again, that's the Fourier transform, right? So that is, if xt, if the signal is ut minus 2, then the Fourier transform of that signal is, therefore if the signal is the delayed version of unit step, then the Fourier transform is e to the power minus j 2 omega 1 by j omega plus pi delta omega, right? But just as an example, if I take the magnitude response, try to understand, this is a complex number, this is also a complex number multiplied, right? So this is going to be, so again, if you recall, if I have two complex numbers multiplied and if I take the modulus of those, then I just individually multiply the moduli, right? That's the property in complex number, property of complex numbers. So here, if I take the mod on everything, right, this, the thing in the parenthesis is a complex number, and this exponential is also a complex exponential, so it's a complex number again. But if I take this modulus, what happens is I have two individual moduli here, this one and this one, right? Now this is just like before, right, when we calculated the Fourier transform for the unit step, right? But this, what is the modulus of this? What is the modulus of this? As a matter of fact, the modulus of e to the power, what is the modulus of e to the power j theta? So what is e to the power j theta? That's cos theta plus j sin theta, right? So what is the modulus of that? The modulus of that would be this, right? So from the complex numbers theory, so the modulus of this quantity is going to be cos square theta plus sin square theta, square root of that, right? So the modulus of x plus jy is x square plus y square whole root, right? That's going to be equal to 1, right? So this quantity has a modulus of 1. So the answer is like, so if I am calculating the amplitude response, the amplitude response would be the same as the amplitude response of a unit step, like without a delay or without an advance. Okay, so this only contributes to the phase term. So this only contributes to the phase. Phase means angle of x omega. So we shall discuss these later on, okay, but just try to understand that, okay? So I think you got this problem, right? Feel free to ask again if you have any query regarding this. Right? So let me know if I need to do another problem on this. Otherwise, we will proceed. Please confirm if you have understood. So this is the thing that you need to understand, that the Fourier transform is this. Yeah, let's do another problem on this. Absolutely. So let's start another problem on this, right? Let's do another example. So let me ask you to calculate the Fourier transform of a very simple thing, delta t minus a. And actually we derived this in the last class, right? Now instead of deriving this today, we are going to use this property, right? And I have chosen this example specifically because we derived this in the last class, right? Okay, we did derive, I mean rather we used this in the last class and we derived it nonetheless, right? So now if I use this property, so what can I say? I can say we know that the Fourier transform of delta t, what was the Fourier transform of delta t? That's just 1, right? That's just 1, right? Then from the time shifting property, what is the Fourier transform of delta t minus a? That's going to be the original Fourier transform multiplied with e to the power minus j omega a, right? So with that said, the answer would be e to the power minus j omega a. And this is in agreement with what we actually did in the last class, right? Right? So, I mean, this is correct, right? So if I know the Fourier transform of the original and unshifted signal, then we can calculate the Fourier transform of the shifted signal as well. Huh? Okay, do you need another example? Would you somehow need another example? Please let me know. Otherwise, we shall proceed with the next property. All right, so let's proceed with the next property. So property number 3, right? So of course we did time shift. Let's do a frequency shifting. Right, so let's do a frequency shifting. So the frequency shifting property, I mean, tries to go back from the other way around. The question is this. So somehow, if x omega is the Fourier transform of xt, then what is that thing for which the Fourier transform is this? Right. Fourier transform is this. So what if there is a shift in the frequency, right? What if this is something like that? Okay, we shall, someone is saying, let's solve another example. Okay, but for that, let me give you a question, for example. Okay, let me give you a question. Try solving that. So exercise problem, for example, it's a very simple exercise. You did ut, right? Try calculating u t plus 3. Try calculating the Fourier transform for that. And let me know if you can apply the property of time shift here. So with that said, so with frequency shifting, so we are trying to calculate the inverse Fourier transform of this, right? What if there is a shift in frequency? So what would happen here, right? Do you understand my problem here, right? So we're trying to kind of find the inverse Fourier transform of this, right? So with that said, let's prove. Again, I don't really recall this. So the proof is something like this. Of course, we are trying to calculate the inverse Fourier transform of this. So we are trying to calculate the inverse Fourier transform of x omega minus a. Right? And those who need another example, try solving this by yourself. Okay, that would clear up the idea, I think. So if I do an inverse Fourier transform, I would have 1 by 2 pi integration from minus infinity to infinity. Of course, x omega minus a e to the power plus j omega t d omega, right? That's the definition of inverse Fourier transform here. Now again, I believe you understand that we are going to apply certain properties, shifting, right? We are going to shift here, for example. So what shifting am I going to use? I'm going to use something like this. So substitution. Substitution. What is the substitution? We are writing omega minus a equal to, say, for example, I don't know, what am I going to write? Omega minus a equal to, say, I don't know, maybe q, maybe something like that. Okay. So of course d omega is equal to dq, and this is just something random I am assuming, right? Okay, and I have to write omega and q. So omega varies from minus infinity to plus infinity. So of course, when omega goes to minus infinity, q is also minus infinity because a is a finite quantity. And when omega goes to plus infinity, q also goes to plus infinity. So I have this, right? No issues with that. So if I do the substitution here, I have 1 by 2 pi integration from minus infinity to infinity and x, and instead of omega minus a, I have q, and e to the power minus j. Now instead of, what am I writing? J omega, instead of omega, I have q plus a, right? Q plus a t, right? And instead of d omega, I have dq, right? So we have just done a substitution. So I have 1 by 2 pi integration from minus infinity to infinity xq, and if I just expand this product, I have e to the power jqt into e to the power jat and dq. Now as far as this integration is concerned, q is the variable in this integration, right? So this term here does not have anything to do with the integration. I mean, it does not have any variable, okay, from the integration, right? So from the perspective of the integral, this term is entirely a constant, right? So it can go outside the integration, and if it goes outside the integration, it becomes simply e to the power jat, right? And we have the rest of it, 1 by 2 pi integral from minus infinity to infinity on xq e to the power jqt, okay, dq. But again, try to understand something, that the Fourier transform, the inverse Fourier transform, okay, try to understand something, that the inverse Fourier transform of xt, of x omega, is 1 by 2 pi integration from minus infinity to infinity x omega e to the power j omega t d omega. But again, since omega is the variable of this definite integral, right? I'm saying definite integral, but it shouldn't really. But anyway, since omega is the variable of this definite integral, it is just a placeholder name. I can write anything I want here. So instead of writing omega, I could write p here, right? I could write q here. I could write anything here, right? Because this is just a placeholder name, right? So with that understanding, I can always write q here if I want, because that's a placeholder name. Because after doing the integration, I'm going to replace q, every location, every appearance of q, with the upper limit and the lower limit. So q will not be there. Just like if it was omega, omega will not be there. right? Only t will be there. So this is again a definition of the inverse Fourier transform. We have just changed the name of the variable and nothing else. So with that said, it is e to the power JAT, and what is this? This is the inverse Fourier transform of the original signal, so that's xt, right? So we have discovered that the inverse Fourier transform of x omega minus a is e to the power JAT xt. So I can say that e to the power JAT xt has an inverse Fourier transform of has a Fourier transform of this. Okay, has a Fourier transform of this. So what kind of example can we think about? So that's called a frequency shifting property. For example, now let me ask you this. Let's do an example, right? Let's do an example. So let's do an example. So we know that the Fourier transform of say we know that the Fourier transform of we know that the Fourier transform of 1 is 2 pi delta omega, right? So I can say the inverse Fourier transform of 2 pi delta omega is equal to 1, right? Fourier transform of 1 is 2 pi delta omega, so the inverse Fourier transform of 2 pi delta omega is 1. So my question is, what is the inverse Fourier transform of 2 pi delta omega plus 2, say? What is the Fourier transform of that? What is the Fourier transform of inverse Fourier transform of 2 pi delta omega plus 2? Now we have a frequency shift, right? So let's go back to the property here. So if this is omega minus a, then this is going to be this, right? So this is xt, this is x omega, right? This is xt and this is x omega, right? So this is omega minus a, right? So technically for us this a is just minus 2, right? Because we derived the property with omega minus a, right? So with that said, this is going to be e to the power j omega a, sorry, jat, right? E to the power jat xt, right? The Fourier transform e to the power jat xt is x, so this is basically x omega minus a, right? This is what it is, right? This is the particular term, right? So with that said, this is going to be e to the power j with a minus 2, right? So j minus 2 jt xt, right? So do you understand this? So if we have such a shift in frequency here, we get something like this. So if there is a time shift, then we get an exponential term in frequency, and if there is a frequency shift, then we get an exponential term in time. Right? Right. So let's do a concrete example here. Another example with this. Okay, another example. I'm asking you to calculate the inverse Fourier transform of, say, what should I ask you to calculate the inverse Fourier transform of? Say 5 by omega square plus 2 omega plus 3. Okay, clear? Let's try finding the inverse Fourier transform of this. yep, let me solve this problem and that will clear everything up here. Okay, okay, that will clear everything up. So what is the Fourier transform, inverse Fourier transform of this? And in fact, as a matter of fact, you are going to see things that are pretty similar to this. You're going to encounter things that are pretty similar to this, for example. Okay, but before I can solve, let me ask you this. What is the, so before I can solve this, I have a question for you. What is the inverse Fourier transform? Actually, we did this in the last class. Okay, what is the inverse Fourier transform of something like this? We calculated the inverse Fourier, calculate the Fourier transform of something that resulted into this. So can anybody tell me what was that thing? What was that thing for which the Fourier transform was this? What was that thing for which the Fourier transform was this? Because I need to know that right now. Okay. Question is, what was that thing for which the Fourier transform was this? Whose Fourier transform was this? Because we did do that in the last class, right? So can anybody tell me what is that particular expression for which this was the Fourier transform? So can somebody go through the notes in the last from the last class and tell me what is the quantity of which this is the Fourier transform? And I'll be back in like a minute. So try telling me that. Okay, it seems like no. This is not SGNT. This is not the Fourier transform SGNT. You might be extremely confused, right? This is not the Fourier transform SGNT. Because I truly remember the Fourier transform of SGNT, right? For signum t, the Fourier transform is 2 by j omega, right? Right? So what is that quantity for which this is the Fourier transform? Do I really have to open the last, open the notes from the last class? Right, so yes. Right. So from the last class, if you go through the notes from the last class, this was the Fourier transform of e to the power minus a mod t, right? Something like that. So the Fourier transform of this was this. That is why the inverse Fourier transform of this is this, right? We know. Not really, Mahesh, you are kind of wrong here. Just go through the notes of the last class, or if you have any query regarding this, please feel free to ask. So now we are going to use this property somehow here to figure out what is the Fourier transform of this, right? So my objective is to calculate the Fourier inverse of 5 by, I'm assuming that this is correct, okay, because again otherwise I would have to derive this once more. So plus 2 omega plus 3, right? So if that is something, then I can write this as Fourier inverse of, so 5 by, so can I write this as omega square plus 2 omega plus 1? So omega square plus 2 omega plus 1 plus 2, right? Something like that can be written. And if I write something like that, so this is then Fourier inverse of 5 by, that's omega plus 1 whole square, and that's root 2 whole square, right? Right? Is that understood? Is that understood? All right. So, and in the numerator, this 5 can be easily manipulated this way, because that 5 is a constant, right? And the Fourier operator is basically a linear operator, right? This 5 can be brought outside, and let me do something here. And here I'm writing 2 root 2, and I'm writing dividing by 2 root 2. A simple division, right? This 2 root 2 will be cancelled out. We have a 5, just as usual. So I can do something like this, right? All right. All right. Right. So now we have to use this frequency shifting property, right? Because this is, look at this one, this quantity. This is quite similar to this. This is quite similar to this. Imagine we did not have this plus 1 here. We just had an omega here. Imagine we just had an omega here. If we had something like this, my question is, what would be the Fourier transform, inverse Fourier transform of that? We had 5 by 2 root 2 outside, and from this a is root 2, right? Then what is going to be the Fourier inverse Fourier transform of that? This would have been e to the power minus root 2 mod t, right? Because of this formula we actually derived in the last class. The Fourier transform of minus e to the power minus a mod t was this, and from that we have this, right? If this was omega, right? This was omega, but this isn't omega, right? So since this isn't omega, this is a shifted version of omega. So instead of omega, I have omega plus 1 here, right? Omega plus 1, right? So instead of omega, I have omega plus 1. So I have to apply this property, right? So instead of omega, I have omega plus 1. So omega plus 1 means I have omega minus of minus 1. So this a in this particular example is plus 1. So in this a in this particular example is minus 1, right? Right? Again, let me tell you, let me go back with this. If this was just omega, this would have been the answer, right? But since this is not, this is a shifted version of omega. So this is omega plus 1, for example. So omega plus 1 essentially means that this is omega minus of minus 1. So that is my a, that's a, right? For that particular example, right? So this is going to be this entire quantity multiplied with what we get from the shift. So from the shifting property in the frequency, so if you have something added or subtracted from omega, if you have a frequency shift, we have to multiply everything with e to the power JAT. So what is a? A is minus 1. So I have to multiply everything with e to the power. So I have to multiply everything with e to the power j into minus 1 into t, right? So e to the power minus jt. So let's do that. Let's bring it out here, and we have to multiply everything with e to the power minus jt. So 5 by 2 root 2 into e to the power minus root 2 mod t, that was the inverse Fourier transform of 2 root 2 omega square plus root 2 whole square, right? And e to the power j into minus 1 into t, that resulted as a multiplication with this because of the frequency shift we have here, right? So with that said, I can now, of course, we have exponentials, two exponentials, 5 by 2 root 2, and I can write this as e to the power minus root 2 mod t plus, sorry, minus j t, something like that. And for this quantity, this would be the Fourier transform. So please do tell if you have understood this, because this is a more concrete example, and this kind of examples are the ones that you are going to encounter quite often later on, okay, while discussing systems and how they interact with signals. And this is in fact quite similar to the Laplace transforms you have studied probably earlier in your mathematics classes, and maybe in circuit theory classes as well. Laplace transform is something that is called an analytic continuation of Fourier transform. Okay, in complex analysis there is a term called analytic continuation. So Laplace transform for the most part can be considered to be an analytic continuation of Fourier transform, kind of an extension of Fourier transform, if you want to say so. Right. So in a sense, Laplace transform can give you more insight about a system than Fourier transform can, but Laplace transform gets overly complicated very quickly. Alright, so do tell me if you have understood this, or if you have any query regarding this. Please let me know if you have any query. Alright. Right. So property number, I think it's going to be 4, right? Property number 4. Let's do that. So it's what should I say? Frequency and time and frequency scaling. So it's two properties combined in one. Time and frequency scaling. My objective is right now to calculate the Fourier transform of xat. So if I know the Fourier transform of xt to be x omega, question is what is the Fourier transform of xat? Again, I do not really recall any of the expressions. Okay, but let's try calculating that. So I am trying to calculate the Fourier transform of xat, and how do I do that? Just by simply applying the definition, right? Of course, we have to do a substitution here. For us, the substitution would be like we are replacing at with p, and therefore a dt would be dp, therefore dt would be 1 by a dp, and with that said, the limits are going to be, so here this is t, this is p. Now we have a situation, right? So the limits are varying from minus infinity to plus infinity, right? So limits are varying from minus infinity to plus infinity. And we have two possible situations. What are the possible situations? We have one situation where, I mean, A is a positive quantity. So let's consider this to be my case 1. Let's consider that to be case 1. When A is a positive quantity, when A is a positive quantity and t goes to minus infinity, right, then P is also minus infinity. And when A is a negative quantity and when A is a positive quantity, when t goes to positive infinity, P also goes to positive infinity. So I don't have any issue. And this is quite similar to a proof we did do for the Dirac delta or unit impulse, right? So with that information, let's try doing this integration from minus infinity to infinity. I have x p, because at is p, e to the power minus j omega. And what is t? T is p by a, j omega p by a. And instead of dt, I would write 1 by a dp, but 1 by a can go outside because that's a constant. We have this. The limits are not changed because a is positive. So this is my case 1 when a is positive, right? So with that said, that's going to be 1 by a integration from minus infinity to infinity x p e to the power minus j. Now try to understand what I'm doing here. I'm just, instead of writing j omega p by a, I'm writing j omega by a into p into dp, right? And again, p is a variable, just a nomenclature, right? That's just a variable used in this, okay, in this definite integral. So that particular name can be changed, right? So without any issue, I can write up that this is again identical to this. Sorry, instead of writing p, I'm writing t, right? Just like before. Of course, that's just a name change, right? No issue. Name change. That's a name change. For the definite integrals variable, right? So the definite integrals variable was p. We just changed the name. Absolutely no problem with that, right? All right. And now let's assume something very interesting. Assume omega by a, that quantity, let's assume that to be, say, q or something like, I don't know, maybe w, right? Maybe let's consider that to be w, right? I don't know. So I have 1 by a integration from minus infinity to infinity. Again, try to understand, omega by a got nothing to do with the integrations variable, right? That's a constant as far as the integration is concerned. So I have xt e to the power minus j wt dt. But if you look closely, this is nothing but the same definition as we had for x omega. But now instead of x omega, now I have x w, right? Because just we have changed a certain name. Instead of writing omega by a, I have written w. And this is just the definition of Fourier transform. Now since I have w here, I have written w here. If I had omega here, I would have written omega here, right? But what is w? W is omega by a, right? So that is what it is, right? So when a is positive, we have just derived that the Fourier transform, when a is positive, that the Fourier transform would be 1 by a x of omega by a. So if I do a free time scaling like that, there's a time contraction. If a is a quantity which is larger than 1, then we would have a frequency expansion. A time contraction results into a frequency expansion and vice versa. Okay, we haven't yet considered the situation where A is a negative quantity. But please let me know if this evaluation is clear so far. Right? Please post your questions in the live chat if you have any query. All right. What about the others? Can you follow this? The problem with this subject, this signals and systems subject, is that you have to be able to follow all the classes, right? If you somehow are unable to follow a certain class, then what happens? Or if you don't attend a certain class, then what happens is for the next classes, you won't be able to understand anything. That is one of the issues we often see in signals and systems. So at the end of the entire semester, we see, only a few people have understood everything, right? So again, I'm telling you the same thing once more. If you have any query, feel free to ask. Okay. Let me proceed only if you are satisfied with the explanation. If you haven't attended the previous classes, all the videos are still available on YouTube. So try following those. I have given you the handouts. Okay. So right, and you can get in touch with me. Just drop me an email. I will respond. Don't worry. Right. So now let's consider the situation when A is a negative quantity. Now this consideration, when A is a negative quantity. So we previously considered when A is a positive quantity. Yes, absolutely. So one of you have already gotten through to this. And if you have recalled what we studied during our physical classes regarding Dirac delta or unit impulse, this is quite similar to that. Okay, as a matter of fact. So we are considering the negative situation here. So the same thing, we are actually calculating this integration. So x of at e to the power minus j at j omega t dt. So we are actually calculating the Fourier transform of x at, right? So with that said, of course, now the same substitution will happen. Only change that will happen is the situation where A is negative. So let's do that here. What if under this same substitution A is negative? What if A is negative? That's my case 2. Case 2 where A is negative. So if A is negative, and if I do the substitution here, T and P, okay, when T goes to minus infinity, right, look here, when T goes to minus infinity, and since A is negative, we have a negative quantity multiplied with minus infinity. So P is plus infinity, right? And similarly, when T goes to plus infinity, I have a negative quantity multiplied here because A is negative right now. Then plus infinity into a negative quantity gives me a negative infinity. So when T goes to plus infinity, P goes to minus infinity. And the rest of it remains the same. So this is case 2. This is case 2. And this was case 1, right? So with that said, if I now do the substitution, the limits will be reversed. This will be from infinity to minus infinity, right? X at would be xp e to the power minus j and omega. Instead of t, I would write t by p. Just t by, what was it? Instead of t, I would write P by A. Instead of writing T, I would write P by A. And instead of dt, I would write 1 by A dp. So I can bring 1 by A outside. I have 1 by A dp, right? So we have taken care of that. So of course, understandably, we can reverse the limits once more by putting a minus sign outside. So minus 1 by A integration. Now it goes from minus infinity to plus infinity. I have xp e to the power minus j omega by A p dp. And I'm not prolonging this explanation any further because this is just like we did before, right? This is that same integral, right? And that eventually results into minus 1 by a x omega by a. You can just go on like we did before. We can do a name change here, and that will result into xt here, for example t, and we can replace omega by a with capital W or something like that. Then I would write xw as the result here, and then w is omega by a, and so is the result, right? So right now we have gone into this result, right? So we have seen that the Fourier transform of xat has two results, right? This is minus 1 by a x omega by a when a is a negative quantity, and this is plus 1 by a x omega by a when a is a positive quantity, right? So what is this? This a can be brought, this minus sign can be brought here, right? So when a is negative, I have a negative sign here. So when a is, say for example, minus 5, I have a minus of minus 5, so plus 5. And when a is a plus 5, I have 1 by 5, so that's a plus 5. So what is this? This is nothing but a 1 by mod a x by x omega by, right? So that's the entire derivation, right? So technically I have a modulus sign here, right? So that's the time and frequency scaling property. It's a time and frequency scaling property, right? All right. So please let me know if you have any query regarding the derivation here. So let's do an example. What example can I think of right now? Okay, let me ask you to calculate the Fourier transform let's calculate the Fourier transform of delta 5t, say. What is the Fourier transform of delta 5t? It's a very simple example for a simple problem. Okay. So of course we know that the Fourier transform of delta t was 1, right? Then the Fourier transform of delta, so that's x omega, right? So this is x omega, right? So 1. So Fourier transform delta 5t would be 1 by mod 5 and x omega by a, but this is a constant that remains like that. So the answer is simply 1 by 5. That's the Fourier transform of delta 5t. Okay. I don't think there is any difficulty understanding this, right? All right. So do you need another example? We shall do plenty of examples like that later on, so that's not an issue, I think. Alright, so if you are able to follow up to this far, I think it won't be very difficult for us to proceed with the next example. So the next one I'm going to talk about is, strictly speaking, not a different property. It's just a corollary of this property number 4. Okay. So which is time reversal. So property number 5 is called, so this is being given a separate name simply because of the fact that this is quite often used in many examples. Okay, this property is time reversal. So the property is for this. So if the Fourier transform of xt is x omega, question is what is the Fourier transform of x of minus t? And without doing anything, without doing any proof, by looking at this one, we can actually prove that. So if I write x of minus t, then a is just minus 1, right? So without actually proving anything, we can write minus 1 here. So I have 1 by mod of minus 1 x of omega by minus 1. So that's 1 and that's minus omega, right? From that previous property, right? So this is x of minus omega, right? So what is this? This is a time flip, right? This is a time flip. So of course, from previous classes, you understand this is a time flip. And what is this? This is a frequency flip. So a time flip immediately results into a frequency flip. That is what it tells me. But this has certain serious implications. Okay, certain serious implications. So let's see an example that would make things clear. So this can be easily proved. Again, let me just write it down. Simply from property 4, right? Okay, right. So this has certain serious implications. I mean, very important implications. Let's dive into those. Say we are now trying to calculate. So no, it's not linearity property. If you're saying it's a linearity property, no, it's not linearity property. This comes from the frequency shifting property. With linearity, I can multiply things with x. Okay, outside. I can do changes in amplitude, not in time, right? If I do some changes in time, that's no longer linearity. Okay, got it? So I can do changes in amplitude, right? I can add things up, I can multiply things, right? I can modify the amplitude, but not the time. All right. So later on, we will actually see that your intuition is kind of correct. If you're saying it's a kind of a linearity property, actually it is sort of, right? And you will see that the Fourier transform is a time invariant operation. From that, you will see that these things are quite, actually easily understandable. Okay. So we are now trying to calculate the Fourier transform of u of minus t. Fourier transform of u of minus t. So what is u of minus t? Of course, u of minus t would be. So what does u of minus t look like? Okay. So u of minus t simply looks like this. Oh, what am I doing? Right? Okay. So that's my u of minus t, right? All right. So we are trying to calculate the Fourier transform of that, but we have to somehow go back to what we know. We know, what do I know? What do we know? That the Fourier transform of ut is 1 by j omega plus pi delta omega, right? Then my question is, what is the Fourier transform of u of minus t? From this property, we know that the Fourier transform of u of minus t would be simply replace omega with minus omega. So I have minus 1 by j omega. So I have replaced omega with minus omega plus pi delta minus omega. But delta is an even function. You people know that. So the answer is minus 1 by j omega plus pi delta omega, since delta is even, right? So therefore the Fourier transform of u of minus t, so time reversed unit step, that's going to be 1 by j omega plus pi delta omega. But again you have to understand that this negative sign is only affecting the phase term here. It is not affecting the amplitude here. If you take a mod, that phase term will automatically vanish. Thus the minus sign will automatically vanish. So if you plot the amplitude response, there is no difference. Okay. So if you plot mod x omega, there won't be any difference, and we will see these things, I mean, in greater details later on. But this class is going to be, I mean, figuring out the mathematics for us, because understanding how to, I mean, solve these would be pretty important. So right now I have an exercise for you. I mean, not a exercise for later on, but exercise for right now. Okay. So if you have understood this far, if you have been able to go this far, so I have an exercise for you. So this exercise problem is this: find the Fourier transform of u minus 2t minus 4. I mean, of course, don't even think about doing it as a using integration, right? Try applying the properties that you have understood so far. And this again kind of links to what we studied while discussing the time domain signal operations, right? Yeah. So I'll give you like 2 minutes to figure it out at least. I mean, you don't have to solve it right now. Just figure out what you are trying to do, what you are going to do if you encounter a problem like that. What you are going to do. Figure that out first. Just tell me the steps or the properties that I'm going to use here right now. So we know, of course, we have to start from you are correct, but your correct answer is in the reverse order. Yeah, so let's see. Yes, you people are kind of guessing it right. So we know what is the Fourier transform of ut. We know that the Fourier transform of ut is 1 by j omega plus pi delta omega, right? That's the Fourier transform of ut. Then what is the Fourier transform of u of minus 2t? Now we are going to apply the property of time and frequency scaling, right? We are going to apply property 4. So what is property 4? Property 4 tells me that the Fourier transform of xat is this. So of course we are now calculating Fourier transform of u of minus 2t, right? So a is minus 2 here, right? So I am going to use that here. Okay, so a is minus 2. So I have 1 by minus 2 mod of that, and all the omegas will be replaced by omega by minus 2. So I have 1 by j omega by minus 2, j omega by minus 2 plus pi delta omega by minus 2. That's from property 4, right? Yes, instead of doing a time reversal, I have just applied property 4 because property 5 is just a subset of property 4, right? So let's not prolong this answer. Yes, you could do a time reversal, then time scaling, then shifting, right? So I've taken care of everything all at the same go, right? So this is equal to 1 by 2, right? Let me just small font, let me write down property 4. We have applied property 4 here. So that's half. And if I just simplify this, this becomes 2 by minus 2 by j omega plus pi delta. And since again delta is an even function, that's this. Right? All right. So I don't think there is any issue with that. But I can now apply certain properties of Dirac delta. Recall delta AT is 1 by mod A delta T, right? So if I use this property, okay, then what do I get? This is half. Again, we did this in our one of the physical classes, right? And this property kind of looks like similar to this, right? 1 by 2 j omega plus pi. So this is delta AT, where A is half. So I have 1 by half, of course, mod of half delta omega. Right? So this can be written as half minus 2 by j omega. So plus 2 pi delta omega. Right? So that's minus 1 by j omega plus pi delta omega. This has a certain significance I'm going to tell you shortly. But this is the Fourier transform of minus 2 ut. Right? This is the Fourier transform of minus 2 ut. Right? So far we have discovered that the Fourier transform of minus 2 ut is this minus 1 by j omega plus pi delta omega. Right? Then I have to calculate the Fourier transform of this. Look carefully what I have here. Okay, look carefully what I have here. Okay, here I have minus 2 ut u of minus 2t minus 4. So that's minus 2t minus plus 2, right? So that's the same thing from here to here. From here to here, what is this? This is a time shift. This is just a time shift. Right? So in Fourier transform, if I have a time shift, I also know what to do here. So time shift by plus 2 units. So here, let's go back to the property of time shift. If you recall the property of time shift here, what is that time shift property? Time shift property. So for example, here. So Fourier transform of xt minus a. Okay. So some changes happen to t. So this t minus a, so e to the power minus j omega a x omega. So I have to just here this one. What have I subtracted from t? So this has to be like t minus a, right? So a is simply minus 2, right? So with that said, of course, let me go back again. What was the property? E to the power minus j omega a, right? Okay. Right. So e to the power minus j omega a, right? And multiply this. So I have minus 1 by j omega plus pi delta omega. And what is A? A is minus 2, right? So A is minus 2. So if I write that, that's going to be 2 omega. So the minus sign cancels out. Right. So that's the entire Fourier transform. So therefore, we have just calculated that the Fourier transform of this is e to the power j 2 omega minus 1 by j omega plus pi delta omega. Right. So, right. Yes, I think. So, are you talking about this one? So you have questioned that why am I putting minus half, minus 2? Oh, this one? Okay, this one is in the property, right? So if you have a negative quantity here, right, automatically I have a minus sign here. So minus 2 will automatically become plus 2. And how does that happen? That happens simply because there is a mod sign like that, right? So if I had minus, so since A is negative, this is the property that is going to be applicable here, right? Since A is negative, I am going to have 1 by minus of minus 2. And that is what we have here. We have 1 by minus of minus 2. That's just 1 by 2. And here we did write 2. So can I do time shifting first? No. If you do time shifting first and then the reversal, this is going to be the same. But you have to keep in mind about the bracket, right? You have to make sure that you put the bracket, right? So that you don't shift it in the wrong way, right? Time shift, amount of shift is associated with time, right? So yes, you could do time shift first and then take about the time scaling. You could do that, okay? But keep in mind about the bracket, okay? So time shift by this much and frequency shift and time scale by this much, okay? So yes, keep in mind about the bracket here, okay? But let me show you an interesting thing here. Something interesting that interested me, long ago. Okay, something interesting. Right. What is the Fourier transform of ut? What is the Fourier transform of ut? That's, of course, already we are quite familiar with this. This is j omega plus pi delta omega. Again, let me tell you if this is understood. If any query, please let me know. Okay, something interesting, right? Okay, question is, what is the Fourier transform of u of 2t, say? What is the Fourier transform of u of 2t? Of course, I have to do a time scaling. So the property tells me it is 1 by mod 2, right? And here I have to replace omega with omega by 2. So I have 1 by j omega by 2 plus pi delta omega by 2. So what is this? This is 1 by 2 and this is 2 by j omega plus, yeah, I have pi delta omega by 2 and here I have this property of Dirac delta, right? So for this is pi into 1 by mod half into delta omega. That's from the property of unit impulse. So I have half 2 by j omega plus this is, of course, this becomes pi, so 2 pi delta omega. So what do I have? 1 by j omega plus pi delta omega. Do you see it? Do you see it? I think you see it, right? The thing is, that is the Fourier transform of u of 2t is 1 by j omega, right? But what is amazing here? The amazing thing that you might see here, might you already have noticed here, is that the Fourier transform of ut is identical to Fourier transform of u2t, and that will be the same if I write u3t, right? Similarly, the Fourier transform of u3t, 4t, 5t, 5.5t or any t, for example, Fourier transform of uat is 1 by j omega plus pi delta omega as long as a is positive. Okay, so if I'm taking Fourier transform on this, okay, if I get to see these frequency constituent components, I don't see any difference. But why do you think that is so? Why do you think that is so, right? Why is not Fourier transform making any distinction between these two signals? So as far as the Fourier operation is concerned, so as far as the frequency components, as far as the constituent sinusoids are concerned, ut is identical to u2t, u3t, u4t, u5.5t, 6.6t, whatever. Okay, as long as a is a positive quantity, it's identical. Yes, absolutely. For the time reversal, would just have a minus sign. Okay, but yeah, the result would be very similar here. Okay, but do tell me, what is the implication of that? Why do you think that it is similar? It is so. Can anybody shed some light on this? Because that's quite important here. The Fourier transform is making no distinction between these signals, as if these signals are identical. So can anybody have some explanation of that? Why that is so? So what is the explanation? The explanation is kind of simple. The explanation is kind of simple, and you might have already understood that ut is identical to u2t, and u3t, in fact u4.5t, anything, uat, as long as a is positive. These are all the same signals, right? Okay, so why do you think that is? Let's draw this, and it's going to be quite evident shortly. Say yes. So nothing changes like that, mathematically speaking, but what technically speaking is this. That's ut, right? That's my ut. That's ut, right? So that's 0, right? So what if I take this signal and what if I take this signal and copy paste it? Okay, not that. What if I take this signal and copy paste it, and I want to calculate u of 2t. So what is u of 2t? U of 2t is a time contraction, right? U of 2t is time contraction. So we are contracting the signal, right? But even if I contract the signal, does anything change? No, nothing changes. Because how is ut defined? Ut is defined in this way, at least for our definition. Ut is defined as this. It is 0 as long as t is less than equal to 0, and it is 1 as long as t is greater than 0, right? Then what is u of 2t? U of 2t would be defined in this way. This is 0 as long as 2t is less than equal to 0, and this is 1 as long as 2t is greater than 0, right? So this is identical to saying that this is this when t is less than equal to 0 and 1 when t greater than 0. So there is really nothing that changes here, right? And so on. So for all intents and purposes, ut, u2t, u3t, u any positive scalar quantity multiplied with t are identical. And that is why even Fourier transform does not do any distinction between those signals. Right. So I think you got that point, right? All right. Yes. Yes, since the signal goes to infinity in this direction and also in this direction, if you contract it, nothing really changes, right? If you contract it about the vertical axis, okay, nothing really changes here, and things contract, things expand, but since it is going to infinity from both sides, nothing really changes, right? And that's the same similarly for 1. So what is the Fourier transform of 1? That's 2 pi delta omega. And if you do the same calculation there, you would see that, of course, if doing a time shift on 1 does not even change the signal, so there is no point of talking about that. But in any case, since this signal is indistinguishable under time scaling, yeah, the Fourier transform also does not do any distinction. Yeah. All right. So with that said, so yeah, we are going to discuss. We are going to end our discussion with a small problem here. Okay, small problem. I am going to ask you to calculate all right. So I'm going to ask you to calculate the Fourier transform of this. So your exercise problem for this class, that's going to be the end of today's class, and we shall have 2 more classes on the properties of Fourier transform. So yes, we are kind of proceeding slowly, so that we actually still get to understand things. So this is your exercise problem, and please consider this as your assignment, because you're actually going to try to solve this properly. And one more thing, I have a proposal for you people. So we are going to arrange certain classes on Python programming, specifically designed towards our particular goal here. Right? We are going to do some mathematics. So understanding how to do mathematics using Python programming. So Python for electrical engineers. So we are going to do something like that. Okay, so please let me know how many of you are, would be interested in this. Okay. So the exercise problem would be, I'm asking you to calculate the Fourier transform. Yes, I shall send you a Google form, so fill that up. So we shall arrange something. So Fourier transform for, okay, let me question is draw the following signal and, okay, let's forget drawing. It will be very difficult for you to draw, I think, with your current expertise. Yeah, let me give you a signal. A to the power minus 3t signum minus 2t plus 2. Exercise, find the Fourier transform of this. Is it encompassing all the properties? Let me see. Yep. So that will be your exercise today. Yeah. So try solving this problem and sending it to me. So I will, so this is just a proposal for this moment. Okay, and in any case, we can arrange 1 or 2 classes for, figuring out how to do these things using a computer, right? Right? Python is a free software, so you can always use that without paying anybody or without violating anybody's copyright, right? So this is going to be the exercise today for you people. So, right, all right. So please, if you have any question, any query, feel free to ask. But this is where we are going to leave this class off. And we shall arrange our next class on Friday. If you have any query regarding any of the things that we actually studied today, please feel free to ask. Right. So yeah, try solving these problems and submitting them by mailing them to me, because those will count as your internal assessment and midterm assessment. So right, those will carry 40 marks. Okay. And we are not still entirely sure what to do about the end semester examination, because we have 60 marks reserved for that. But if somehow the lockdown proceeds even further, because the situation is not improving at all, okay, we probably won't have any written examination. If the lockdown goes beyond like June or something like that, there is still a possibility, however bad, but there is still a possibility, because the coronavirus situation is not going down, right? It's going up. So yes, so there is no point of assuming that things are going to be smooth like after a certain point of time, right? Something like that. So yes, so if we have to somehow arrange some online examination, we shall have to figure things out accordingly. So try submitting the assignments, submitting all the problems that I gave you earlier, because that will carry a certain amount. I mean a huge amount of marks for that. Okay. In any case, feel free to ask any question if you have. If you have some question, if you get some query raised later on, feel free to drop me an email. I shall be sending you the answers without any issue. Right. So with that said, let's end our discussion today. Okay. Thanks, and we shall see you in the next class on Friday. Thank you.